All right, folks. So in this video, I wanted to talk about our third type of differential equation that we're going to have in this class, which are called exact differential equations. And so just a little bit of theory before we do an example. We've talked about separable differential equations where you get all the y's on one side and get all the x's on the other and then integrate each side separately. That's nice. We talked about homogeneous or homogeneous, if you like to call it that, where you can write it as a function of y over x and use the substitution v equals y over x and solve it. There's a third type that you'll see, which looks like this. You have your derivative plus a function of x times y equals another function of x. And if you look at this here, it's not separable because you're not going to be able to get the y separated off of the p of x without it attaching to the q of x. It's not a function of y over x. And so you do a different trick, which is called an integrating factor. Basically, what you do is you turn this into something where the left side is the product rule. And so remember, the product rule is the idea that you have f prime times g plus fg prime. And so it turns out that if you multiply everything by a very specific thing, it'll turn into the product rule. And so I want you to think about what can you multiply by that stays the same, almost the same, when you take its derivative. And because the reason we're multiplying is to make it into the product rule. And then the clue is that it's something that stays almost the same. And if you think, oh, what stays the same with its derivative, you should think it's e to the x. So I'm going to multiply everything not exactly by e to the x, but by e to the something. And what I'm going to try to do is deal with this p of x. If I tried multiplying by e raised to the p of x, though, the problem is I would end up chain rule. The derivative of e to the p of x is e to the p of x times p prime. I don't have any p primes in my original problem. But I know that if I take the antiderivative of p of x, then the chain rule will cancel that integral I just put up there, and it'll pop out an extra p of x. Okay, so watch what happens if I take my original differential equation here and multiply everything by I. Now I get e to the integral of p of x dx times dy dx. So I'm distributing it out. I have e to the integral of p of x dx times p of x times y equals e to the integral of p of x, dx should be up there, times q of x. Now, when I first learned this, it's like, that just made everything a whole lot worse. Now we have e's and integrals and p of x's, and it's just, why is that better? What I want you to notice, though, is that the left side is actually a product rule. We have here f times g prime. So f is this first chunk, g prime is the second part. Look here, this is f prime times g. And that's wonderful. What we know is that if you take the derivative of one function times another function, you get that f prime g plus fg prime, or the order I wrote it down there. So what we can do now is say that this really is the derivative of e to the integral of p of x dx times y. So now you've got it down to a form where you can integrate this side and integrate this side with respect to x. Everything on this side is all in respect to x. And here, your integral and your derivative cancel out. So a couple things I'll mention. You have to actually know how to take the integral of the right side of the equation. So that, is not obvious that you'll actually be able to take the integral of the right side. E to the integral of p of x dx, and then times q of x, and then have to take the integral of that. Sometimes things cancel out nicely, but a lot of times you have to use substitution, integration by parts, some other things like that. And then when you actually solve for it, you're going to divide both sides by this term right here. So that's the big picture theory behind how this technique works. It works sometimes. It works when you are able to get an equation in this format that we started with, and when you are able to actually compute I, and when you are able to compute this integral down here. So with differential equations, there's no guarantee you'll actually be able to solve them. So this is just one of the techniques we're learning to solve them: the separable, the homogeneous, and then now the exact differential equations. Okay, so that's it for this video. In the next video, I'll show an example.